Alright, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. We meet again. So for this video, I will explain to you three types of functions. The first one is the injunctions or one-to-one function, and then we also have onto functions or surjections, and then we have a bijections, which consists of one-to-one as well as onto functions. So first, the definitions of the one-to-one functions. It's what we meant by the function f or one-to-one function or injection is if and only if the function of a is equal to function of b, implies that a equal to b for all a and b in the domain of f. A function is said to be an injective if it is one-to-one. So alright, the simplest way to understand this is by using the ordered pair. Alright, so if you still remember, the ordered pair is alright, not by using the ordered pair, but the simplest way to understand this definition is by looking at this figure here. So if you notice in this figure, we have two unempty sets. This is the set A, then this is the set B, and both set has one-to-one relation. And if you see here, the element in set A has only one relation with set B. Same goes to element B. Element B has only one relation to element in set B, which is 5, and same goes to C and same goes to D. So the easiest way to understand this is by looking at this figure here. Alright, this figure. So it is straight away you can see that alright, this function is one-to-one function. Alright, and the second way to understand this definition is by using an ordered pairs. So the ordered pairs, which is this one, A in this element A in set A, and the B, which is the element of set B, then you can notice that for the function to be said as one-to-one function, the B must have only one value. Alright, I give you an example. If let's say we have an ordered pairs, something like 1, 2, then 1, 2, and then we have 2, 1, and we have 3, 2, and yes. So alright, so basically this is this is function 1, 2, 2, 1, and 3, 2. But if you notice here, alright, this B, the image value here exists two times. First in here and second is in here. So if we draw this diagram, so the first set is 1, 2, 3. Let's say this is the A set, and this is the B set. And B we have 1, 2. And if we do the diagram, it will link this one 1 to 2, 2 to 1, and 3 to 2. Alright, so because of this, sorry, I think I should use the weight. Because of these relations, so now these sets is not 1 to 1. Okay. If we remove these pairs, alright, if we remove these pairs, then now it become 1 to 1. Alright, so these are the definitions of the one-to-one function. So we go to the exercise here. Alright, for the first example, determine whether the functions f from a, b, c, d to 1, 2, 3, 4, 5 with fa equal to 4, fb equal to 5, fc equal to 1, and fd equal to 3 is 1 to 1 or not. So, alright, so show. Okay, alright, so so now, okay, so now we have two functions here. We have two sets here, a, b, c, d, and 1, 2, 3, 4, 5. So the set A is A, B, C, and D, and the set B is 1, 2, 3, 4, and 5. And the relation here is A to 4. So A to 4, and then B to 5, and then C to 1, and then D to 3. Alright, so basically from this figure here, you straight away can see that these functions, the function here, is a one-to-one function. Why? Because all element in A has exactly one element of B. Alright? So this is one-to-one. So we see our second example here. Alright. Alright, so now I take our second exercise here. Alright, so in this case, alright, so now we have this one, the first, let's say the function is the set is a value of integer. Okay, integer. So the x is the integer. Alright, so we have sets of integer, and the image of this set is integer to the power of 2. Alright, now, so we have a set of integers. So let's say we have a 0. So 0 to the power of 2 is 0, and 1 to the power of 1 is 1, and then 2 to the power of 2 is 4. And since that integer has a negative value, so we can have a minus 1, and minus 1 to the power of 2 is 1, minus 2 to the power of 2 is, is 4. Alright? Okay, right. So now, So now 0 is 0, 1 is 1, 2 is 4, and minus 1 is 1. Minus 1 is 1 and minus 2 is 4. So for this example, you can see from this diagram that for one value in the image or the codomain, there are two values of x. This is one and this is another one. So if we present this presentation into ordered pairs, we will get 0, 0, and then we get 1, 1, minus 1, 1. We get a 2, 4, and minus 2, 4. So from this ordered pair also, you can see that this image value exists in two different x values. Same goes to here. Alright? Okay. So for the last examples, you may check. Okay? Alright. This is because we say that the set is the integers. What happens if we change these sets into a positive integer only? Alright, so basically, every time when we change our sets, then the function will become a new function. For this case, if we change from the set of integers to a positive integers, so now it will be a different stories. Let's say the x is an element of a positive integer, and the image is the x to the power of 2. Right? So now we have 0, and we will only have 1, which is 1, 2, 3, 4, so it become 9. Sorry. Alright, so for this case, when we change our set, now this relation becomes a one-to-one function. So one-to-one function. This is not one-to-one function. Alright, so you can see the difference. Every time when we change the sets, then the function will be a new function. Okay, so now we go to the surjections. Surjections, a function f from A to B is called onto, or surjective, if and only if for every element B, there is an element A and A with f A equal to B. A function is called a surjection if it is onto. Alright. Alright. For this case, for the injunction, for the one-to-one, you have to make sure that all element in A, in domain, has a pair, has only one pair here. It's compulsory to check and to see all of the element in this set has a pair. Whereas for the surjection, it is compulsory for you to check the element of B here has connection with here. Alright, that's why in the definition here you can see that the function is called as onto if and only if for every element of B, in B, this one, there is an element A and A. If FA equal to B. A function is called a surjection if it is onto. And you can see from here, for all Y, this is Y. Okay, this is actually the F A equal to Y. Okay, for all Y, there exists an X for X Y equal for X of F equal to Y, where the domain for X is the domain of the function and the domain for Y is the codomain of the function. Alright, so this is the way to show that F is one-to-one or onto. So suppose that F A to B, to show that F is injective or one-to-one, show that if Fx equal to Y, Fy for arbitrary x, y in A with x is not equal to Y, then x equal to Y. Okay, so if Fx is equal to Fy, for any value of xy in A and x is not equal to y, then x must be equal to y. Okay, so this is the definition. So basically you can use this type of examples, alright, to show, to prove that it is injective or not. Alright, okay. Alright, so if it is not injective, then you find particular elements such that x is not equal to y and fx is equal to fy. For the surjective, similar to injective. So for this example, let f be the function from a, b, c, d to 1 to 3 defined by this, and check whether it is onto or not. So now we have two sets of functions. We have a, we have b, we have element C, we have element D, and then we have element 1, 2, 3, and then FA equal to 3, B is 2, C is 1, and D is 3. Okay, so we may check, is this an onto function? First thing that you have to see is you must look at into this pipe. Wait, let me check. Let me change the color. First thing, to check whether the function is onto or not, you have to see the y here or the codomain here. So you must have to make sure that all value here has a partner from this pipe. If let's say you have another one which is 4 and 4 is not related to any here, so obviously this is not onto. But since in the example it only has up to 3, so and all these 3 is connected to the domain here, so this is the onto function. Onto function. Alright, because all 3 elements of the codomain are images of elements in the domain, And if let's say the 4 is sensitive, then F will not be onto. For the bijection, alright. For the injection means the function is 1-to-1. For the bijection, for the surjection, the function is onto. Bijection, the function has both characteristics. Alright, so we call the function as a bijection if it is 1-to-1 and onto. Like in this case, right? In this case, you have to check whether this function is 1-to-1 or not. So you can see that all the elements in A here is connected to element of B. So the first first condition for the 1-to-1 is fulfilled, and the second thing that you have to see that all the element is connected once to the B. Alright, so it is 1-to-1. So now, to check that it is onto, then you have to check that whether B, all the elements in B is connected to the A. So we check it. So yes, so we can see that all the X, Y, Z, W is connected to an element of A. So basically this function is 1-to-1 function. Alright. Okay, so these are the list of example that you can see. This is 1-to-1, but this is 1-to-1. For this one, it is a 1-to-1 because all the elements in the domain is connected to the codomain, but it is not onto. Why? Because there is one element in the codomain here that is not connect to any element here. Alright. And this function, it is onto. Why? Because we can see that all the elements in the codomain here is connect with the element here, with the element in the domain. And it is not 1-to-1 because if you see here, for the image, the image value has two elements of domain. So it is not 1-to-1. It must be 1-to-1, right? So this one, it is 1-to-1 and onto. Why? First, you can check the 1-to-1. So all these element is connect to the codomain, and then there is no two values of codomain for one value of domain here. So it is 1-to-1. And onto, you can check that all element in the codomain has relate to one element of domain here. This one, it says that it is not 1-to-1 or onto. So now we can see for the 1-to-1, why it is said that it is not 1-to-1? First, all element here connect to here, fine. But there is one value in the codomain that has two values of domain here, right? 2 has A and C, so it is not 1-to-1. Why it says it is not onto? Because this value of 4 has not connect to any element in here. Okay, so this is not onto and not 1-to-1. It is even not a function. Why? Because one domain has two codomain value, which is this one is, it is not even a function. Okay, so it is irrelevant actually to have one domain, and this one domain has two different codomain value. Okay, alright. And for this operation, I think I will do. Oh yeah, I think I can just. For this, okay, for this one I can just proceed. So this is an operation let f1 and f2 be functions from a to r, then f1 plus f2 and f1, f2 are also functions from a to r defined for all x in a by this operation. So f1 plus f2x is equal to f1x plus f2x, and if it is a multiplication, f1 f2x and f1x multiplied by f2x. So we go into the examples here. Let f1 and f2 be function from r to r such that f1x is equal to x to the power of 2 and f2 is x minus x2. So what are the function of f1 plus f2 and f1 multiplied by f2? So now we see that to do this one, f1 plus f2 here, then will be f1 is x squared plus x minus x2. So we left with an x here. Same goes to f1. This is f. I'm sorry for my hand writing. f1, sorry, f1, f2. Is equal to x to x minus x2. Then you will see this result. Alright, similar as this one. So it become x3, x to the power of 3 minus x to the power of 4. Showing that f is onto function. Oh, basically this is similar as before. So yeah. So for the inverse function, I will do another video. Okay, so it's easy for you to understand, hopefully. Alright, thank you guys. Bye. Alright, bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and a very good morning. So in this section, I'm going to introduce to you an inverse function, but I'm pretty sure that all of you in the class very familiar with this term, the inverse function. So basically this is more likely to revision sessions on what is inverse function. Alright, so before I proceed, all the notes in this video has been extracted from a book entitled Discrete Mathematics and Its Applications, 7th editions by Rosen. Right, so just proceed. So these are the definitions of the inverse function. Let f be a bijection from a to b, then the inverse of f denoted by this presentation is the function from b to a defined as this inverse function b equal to a if and only if f a is equal to b. No inverse exists unless f is a bijection. Why? Alright, so this diagram here illustrates what is an inverse function. So basically, this is the presentation. This is the representation of a function. Okay, so we have fa equal to b. This is so this is the common presentation of the function fa oops it's a bracket, right? So fa equal to sorry, not y, but it's b here. Alright, so or this also can be written as f of x equal to y. Basically, it's just the same, just the variable is changed from a to x and from b to y. Alright, so in this case, if you see here, this is the set of a, this is the set of b, and the a here is the element of set a. The small a here is a element of a set a, and the small b here is the element of set B. Alright, so now you have this element, the A element here, and function of A is equal to is map. Okay, this function, the f here, is used to map an A to a B. So that's why we get this presentation FA equal to B. And then from here, the inverse of B, alright, the inverse of B is actually equal to A. So we have A here, and the small a is in the set of A. By having a function here, we map the A to a B. So we get B is equal to function of A. And then the inverse of this function, which is the inverse function of B, we get back the A. So basically, this is the diagram to present what is the inverse function. Alright, so now the phrase here, no inverse exists unless f is a bijection. So remember the definition of bijection. Bijection means that the function must be one-to-one and the function must be onto. Alright, so if we look back into what is one-to-one, so let's say we have A, B, C. A, B, C is the element of set A, let's say. And then we have 1, 2, 3. This is the set B. Right? So now, and we assume that this function, this function of A and B is one-to-one. Alright? And we also assume that both is onto. So this basically present that this is the function of A to B is bijection because it is onto and is one-to-one. So the reason why the function must be bijection, only then it can get the inverse, because for this case, let's say we take this one, f A is equal to 1, right? So the inverse of f1 the inverse of 1. The inverse of 1 is equal to A. Alright, so let's imagine if, let's say, this function is not bijection. Alright, it's not bijection. Let's say the function of f is, we have A, we have B, and we have A, B, and C. We have 1 and 2 and 3. Let's say we have this one, A, FA is equal to 1, FC equal to 1, F2 equal to 2, FB equal to 2. So in this case, this is not a one-to-one, not. And also this one is not. Alright, let's say I'm giving you an example where it is okay, just give you an example. If let's say it is one-to-one, another one, it is not one-to-one but it is onto. Let's say in this case it is not bijection but then it is onto. Alright, so in this case it is onto. So if let's say, okay, I will write it in this form, f A equal to 1 and FC is equal to 1. What will I get if I inverse the function. There is no value. There is no elements in A that I can assign to the inverse function of 1. So that is the reason why it is important for the inverse function to be bijection. Alright, so, and I give you a second example where this one is onto, tapi dia bukan onto one kan. Ini dia adalah, if it is 1 to 1, it is 1 to 1. No, I want to make it 1 to 1. So cannot, because the definition of 1 to 1 is cannot. It must be like this. So I cannot give you an example of if it is 1 to 1 but it is not onto. I cannot. So I will stop here to give you an example about these things. But by the way, so yeah, I just wrap this. Right. Anyhow, for the inverse function, it is very important to be for the function to be bijection. Means that it must be onto and it must be 1 to 1. Alright. So this is another presentation of inverse function. Alright. So this is the common. We have the function is related from between A and B. Alright. So FA is equal to Y, FB is equal to W, FC equal to X, FD equal to V, and the inverse function means that now we are talking about inverse function of B to A. This one function of A to B, so this one is inverse function of B to A. So so now the arrow also become different. So now we are moving from the B to the A. Alright, so these are the example. Let F be the function from ABC to 1 to 3 such that FA to FB3, FC1. So now we have two sets. We have elements of A, B, C, and we also have 1, 2, 3. Right? 1, 2, 3. So now FA is equal to 2, FB is equal to 3, FC is equal to 1. Alright, so the very first thing that you have to do before you can proceed to find the inverse of F is to check whether it is bijection or not. So the bijection means that the function must be onto and 1 to 1. So the first condition, it is an onto. Why? Because all elements here all element in a codomain has an element in domain. So the first onto is satisfied, right? So what about the second condition? The second condition is 1 to 1. So basically, if you can see here, all elements in the domain and all element in the codomain has one relation. Alright, so obviously it is 1 to 1. So basically, this function is bijection. Alright, so to find the inverse, so now we have FA equal to 2. So the inverse of 2 is A. The inverse of 3 is B. The inverse of 1 is C. So these are the answers, right? So now, yeah, there's an answer here. Right. So now we are moving to this presentation. Let F is integer number be such that fx is equal to x plus 1. Is f invertible? Then if so, what is its inverse? So in this case, alright, in this case, we can let f of x is equal to y. Alright, and then the y is equal to x plus 1. So now we want to find the inverse of y. How to do that? So now we move the x to the y. So now x become x here and y become y minus 1. Alright, so inverse of y is equal to y minus 1. Okay, so what I can get this because it is confirmed that this function is bijection. You may check this by your own. Alright, okay, so for this case, I want you to try, and if you have any problem, you may come to my room and we can discuss. So the first thing that I want you to check is whether this is invertible or not, and if it is yes, then what is the inverse, right? And if you think that this is not invertible, then you may provide me with a justification why you say so. All right. That's it. Alright, so I continue with this part, composition. So in here, what we have is we compose actually two functions together, and let's say the function of f connect the B to C, and function of G connect the A to B. So the composition of F with G denoted by F small dot G is the function from A to C, and it is defined by this presentation. So F not G A is equal to F G A. So what we have here is that whenever you come across with this presentation, what you have to do is you have to solve this part first, the inside function first, and then you bring and then you solve the functions at the outside, right? So basically what we have here is that we combine three sets together, and then what we have here is we have set A, we have also set B, and we have set C. So this diagram here actually illustrate what is this presentation all about. So as I mentioned just now, you have to solve this inner part first. So in this set, there are one element and A, and then by having the G, then we can have the B. So G of A is equal to B. Alright, and then by using this GA, okay, this GA will be transformed to C by using the F. So now to transform from B to C, we have this presentation. Alright, we have F, G, A. Alright, so basically this is what all about. And the F not G is actually combine all these three sets together. The operation here. Alright, so if you can see in this example here, we have A, B, C. So from A, the function G will be used to connect it to B. So that's why we get GA is equal to Y, GB is equal to W, GC equal to X, GD equal to W. And then in here, the F will connect this element in the B to the C, and it will get FB, which is actually the GA. We can write, this is actually can see as G, something like this. Alright, and then the F will transform the B here to the C. Alright, so the FB, which is V, will be equal to I, F, W, FB, BH, X will be I, FY will be J. And then we hide this part, and you can get this. So the A will go to the J because A, Y, and then Y to J. So now A to J. Same goes to B. B go to the W first and then go to H. So now B go to H. And C go to I and D go to H. Alright, so the example here. If fx equal to x squared and gx equal to 2x plus 1, to find the fgx, the first thing that you must do is f, and then what is gx? Gx is 2x plus 1. So replace 2x plus 1, replace the gx to 2x plus 1, and then fx is x squared. So the x in this function of f is actually 2x plus 1. Alright, so now, and the x is x squared, so 2x plus 1 squared. So this is the result for the case of fgx. So what about the case of gfx? For this case, G, and then you have to solve the inner part first. So the fx is x squared. Alright, so the G here is x, and it is present with x squared, right? So now the gx, which is 2x plus 1, so now x is x squared, so now it becomes 2x squared plus 1. Why it is x squared here? Because now in here it is x squared, right? We have another example. Let f and g be function from the set of integers to the set of integers defined by fx equal to 2x plus 3 and gx 3x plus 2. What is the composition of f and g, and also the composition of g and f? So the composition of f and g, f, g of x is equal to f gx So now it is f. What is gx? Gx is 3x plus 2. What is fx? Fx is 2x plus 3. So now the x here is replaced with 3x plus 2. So now we get 2. Then the x is 3x plus 2 plus 3. So now we will get 6x plus 4 plus 3 equal to 6x plus 7. Right? And you can try for the GOF here. Alright? Okay. Okay. Function, inverse, and composition. Consider the following. FA equal to B, and inverse of B, we get an A. And now we have inverse of F, the composition of inverse of F with a function F in A is equal to this. Alright, because F is equal to B. So yes, we get it back A. And F consequently. So I think for this part, I will make another video. Be easy for you. Okay, so yes. Thank you.